All right, so having said that, let's start with part 2 about optimal join algorithms. So I'll talk about what are possible lower bounds and how can we meet them if we have an acyclic join query. What happens when queries become more complicated and have cycles? How do we deal with those cycles using tree decompositions? And then we take a little look beyond what we've discussed here, just to summarize some of the other ideas that are floating around these days. So Wolfgang alluded already partly to that, but what are the queries that we consider? We're looking at what we formally call full conjunctive join queries. You can think of them as just natural joins. So we're joining several relations with each other, and we only consider equijoin conditions. And the resulting relation has all the columns of these incoming input relations. And whenever there's the same attribute name in multiple relations, like in this case, for instance, R1 has A1, R2 has A1, and R4 has A1, then this encodes an equijoin, and only one instance of this A1 column appears in the final query result. Here we use L to denote the number of relations that we're joining. Each relation has order n tuples. And so when we look at the type of query, in addition to joins, we can also have selection conditions, like for instance, an attribute value A4 less than 1. And so these are conditions that are anything where an attribute is compared to some constant or some function of some constant. For full conjunctive queries, we do not consider projections, and that's something that we briefly mentioned for the extensions in the end of the talk. The query size here is order L. This is essentially the size of the query string. So this is not the output size, this is how many relations are participating in that join. And for the output cardinality, we're using R like result size. The other thing that's important to note is we don't assume any pre-computed data structures or indexes. So if an algorithm needs anything like that, it needs to compute it itself and it will be charged for it. So all the cost models that we have here include that kind of pre-processing cost as part of it. In terms of how we measure complexity, Wolfgang also mentioned that briefly, we're using the standard O and omega notation for upper and lower bounds, and we're using that RAM model of computation, which is the thing that everybody's probably familiar with from a standard algorithms class. Here we focus as database people on data complexity, which means that essentially query size is a constant. To see an example of what that means, for instance, here we have O of f of L times n to the power of some function of L. That f of L term disappears, but in the exponent, of course, it does not disappear, right? So it's the same as any constant in an O notation formula. And similarly here for the log n term, that exponent f of L remains. So that simplification does not get rid of all the dependencies on query size. We also follow common practice in these kind of optimal join algorithms and essentially only use the soft O notation for any kind of non-trivial algorithms. And that soft O notation gets rid of polylog factors and input size, which helps make the formulas more readable. And it also hides some kind of more complex subtleties about, for instance, does the hash index have constant time? Is it amortized constant time, expected constant time or not? In this case, we can simply say we do sorting. And for instance, in this kind of soft O notation, sorting has just linear cost because the log n factor disappears from the cost model. So in our example here, this term log n to the power f of L completely disappears because it's a polylog factor in input size. All right, so let's move ahead, right, and see what is the lower bound for query cost in this RAM computation model. Not only conjunctive queries, but any query, if you don't have anything pre-computed, you have to read every input value at least once, and you have to output every result tuple. That means no query can do better than omega of n plus r, right, where n is the input size and r is the output size. It seems pretty hard to match that, this kind of idealistic bound, but somewhat surprisingly, this well-known Yannakakis algorithm, for acyclic conjunctive queries, it can get pretty much exactly that time complexity, O tilde of n plus r. Right, so modulo a log factor, it actually reaches the lower bound. How does it do that? I'll tell you a little more about acyclic versus cyclic conjunctive queries. For now, let's just assume these are the easier types of queries, but they're very common in practice. So given such an acyclic conjunctive query as a rooted join tree, this Yannakakis algorithm has two phases. In the first phase, it does a semi-join reduction, first bottom up from leaves to root, and then back from the root down to the leaves. This semi-join reduction is removing all the input tuples that are not participating in the output. And then we just run a standard join plan, which goes bottom up, joining relation at a time, like any kind of database would do. So how does this look like? Let's go back to our four relation example. Now with some numbers. On the right, you see this tree here. R1 is the root, R3 and R4 are the leaves, and there's a bunch of tuples in there. And you can see also the joining attributes marked up on the links between these tables. So what happens during the bottom-up semi-join traversal? So let's start with R2 semi-joining against R4. Conceptually, we're sending a message from R4 up the tree to R2, and that message contains all the A1, A2 combinations that R4 contains. Right, these are 110, 120, and 220, and R2 uses these combinations to eliminate anybody who doesn't match. Right, so in this case, the bottom three tuples can get eliminated because they can never join. They can never be part of the final result. Then we do the same, sending from R3 to R2 a message about the A2 values. And now nothing happens because already R2 contains only values that also appear in R3. And finally, R2 sends a message with the remaining A1, A2 combinations up to R1, and that results in one more tuple getting removed from R1 in this case. This completes the bottom-up phase, and now the same happens top-down. Right? R1 sends its A1, A2 combinations to R2, R2 sends its A1, A2 combinations to R4, and its A2s to R3, and this results in two more tuples being removed in R1, in R3, and in R4. Right, so after these two semi-join sweeps, we're left with smaller relations, and we run a join bottom-up on those relations. For instance, joining R2 with R4, joining that intermediate result with R3, and then that with R1. So in addition to removing tuples and making the relation smaller, what is really important about this semi-join reduction is that afterwards, every tuple, whenever we have an intermediate join step between some intermediate results with another input relation, it turns out that every tuple on the left joins with at least one tuple on the right and vice versa. And that is actually really important when we look now at the properties of the Yannakakis algorithm. First of all, the semi-join sweeps take order n, so it's very cheap to do that. Now, in terms of these join steps, always guaranteeing that everybody has at least one join partner on the other side. That means that no intermediate result can be larger than the final result, because in every step, the result can only grow. Right? And this is really important because now we know that none of the intermediate results can be larger than R, the final result size. And that means every intermediate join step is between an input of size n plus R, order n plus R, and creating an output of size order R. So given input of size order n plus R and output of size order R, we can use a simple algorithm like sort merge join to compute that result in order n plus R, right, in soft-O notation. And that's exactly how the Yannakakis algorithm achieves its performance, right? Because it has this good property that any of these intermediate results are not larger than the final result. And for that to happen, it does not hold for every possible tree. In this case, it held for the tree that I showed, but in general, it has to have what is called the attribute connectedness property. And I'll talk about that a little later. So this was a good example when we have an acyclic conjunctive query. And now what happens if we have cycles, if we make the query a little more complicated? Let's look at a simple example here. So I'm not going to show a formal definition of acyclic versus cyclic queries. Instead, let me just look at an intuitive way of looking at these types of problems. Think of it like a graph pattern search, right? On the left, we have a three-path query that is looking for three, think of them like edges that are connecting on the endpoints with each other. Right? And this is a join between R1, R2, and R3, where the corresponding endpoints are matching. On the right, the query looks almost the same, but now the cycle is actually closed. So A1 has to match between the R1 and the R3 tuple. So it looks very similar, but what happens when we run a join there? Let's look at an example here. So we have an input table, R1 here, R2, and R3. They're already semi-join reduced. Notice that the right column in R3 has a star because it could be either A4 or A1. Right? So instead of showing it twice, I just mark it up as a star. And let's look at a join tree like R3 being the root of the tree, then R2, and then R1. If we now follow the Yannakakis algorithm on that input, turns out that everybody from R1 joins with everybody from R2, creating n-squared intermediate results. Now that's not a problem for the path query because it turns out they're n-squared final results anyway, n-squared path. So that intermediate result, like in the example I showed you before, is not larger than the final result. But for the 3 cycle, like the triangle, it turns out that there are only n results in the end. Oops. And that means we have an intermediate result that is n-squared, even though there are only n results in the end. So what happened? But this is exactly the attribute connectedness property that is missing in the second example, right? Attribute connectedness means that if we have a tree with these different relations, we have to guarantee for every attribute that all the nodes containing it are connected to each other. So if you look at the 3 path, it is satisfied here. The A2 and A3 cases are both connected. On the right for the 3 cycle, we can see that A1 is not connected, right? R2 in the middle does not contain A1. And so we do not have the attribute connectedness property. And that's the problem. So now the question is, maybe it's just a problem of the Yannakakis algorithm, right? Maybe we just need a better algorithm. And in some sense, that's true. But it turns out, as Ngo, Porat, Ray, and Rudra have shown recently, in general, it is not possible to meet that lower bound of n plus r unless some well-accepted complexity theoretic assumptions do not hold. So pretty much it is believed that it is not possible to reach that n plus r lower bound for cyclic queries, general cyclic queries. So what can we do? There's a class of algorithm called worst case optimal join algorithms. Instead of guaranteeing n plus r running time, they guarantee n plus RWC. What is RWC? That is the worst case output of a query queue over any possible input. So maybe on a given input, that query has 0 output tuples, but still the complexity of the algorithm depends on the worst case output, which could be something like n cubed, n squared, or much larger than the actual output size. So for instance, in this case, for the 3 cycle, it turns out there can be up to the n.1.5 possible output results, n to the 1.5 possible triangles. How do we know that number? This is the famous AGM bound. So it has been shown that there's a way by looking at the fractional edge cover of a query hypergraph to determine what is the largest possible output size of such a query. And as I said before, for the 3 cycle or triangle, this is n to the 1.5, which is already much better than n cubed, which would be a naive upper bound if we just say every tuple in one relation joins with every tuple in the other and so on. Right? So for that specific query, this bound is actually a strong improvement. Now, can we do better than that? It turns out if we use tree decompositions, we could do better than just using a worst case optimal join on the full query. And the main idea is basically here that we put a little more effort into the pre-processing step. And that little effort pays off in terms of avoiding these large intermediate results. In general, the goal is to get a running time guarantee of the type n to the power d plus r for the smallest possible d. And so if you compare that to the worst case optimal joins, instead of having now a complexity that depends on the worst case output, this is now an output sensitive complexity, right? So that r is the actual output size of the given query on the given input, not of that query on some arbitrarily large, on some input that produces a much larger output. And intuitively, this n to the power d captures the pre-processing cost, that extra investment that we have to make. And as we have seen before, if we use the Yannakakis algorithm on acyclic queries, d equals 1, and we get our lower bound. And now, how close to that can we get if we have an arbitrary cyclic query? And this is where tree decompositions come into the picture. Again, I'm focusing here on the intuition instead of showing some long definitions. There's actually papers mentioned in our tutorial paper also that are showing where to find more technical details about all these problems. So what is the big idea about tree decompositions? Essentially, we take a cyclic query. Here we have a 6 cycle between 6 relations, R1 to R6, that are joining on these common endpoints. Right? So think of it like a 6 cycle in a graph, for instance. The decomposition step turns that into some kind of tree structure. Right, so in this case, we have 2 nodes that are connected to each other. One contains R1 to R3, the other one contains the remaining 3 relations. We materialize these nodes that are called bags. Right, in this case, we have, let's say the first one is S, the second one is T. As a result, we get now a simple query between relation S and relation T. This is an acyclic tree, right? This is a tree again. And we can run Yannakakis on that tree and get our guarantee. But now instead of that guarantee being in the original input size n, it is now in the size of the largest bag that we have created. So if, let's say, S is the larger of the two bags, has a size of x, then Yannakakis would run in time order x plus r, where r is the output size of the query that was initially given to us. All right, so this is really important. So this part here, we go from a cycle to a tree and then run Yannakakis on that tree to get our performance guarantee. Now the question is, how do we find tree decompositions and which ones are the best ones? In this tutorial, we don't really have time to go through all the different algorithms and types of guarantees that these decompositions can achieve. So let's look at some intuition what could happen in practice. So again, we have our 6 cycle, joining 6 relations. And what is really important to get these Yannakakis properties that we showed you in the beginning is, one is for correctness, every relation has to appear completely in some bag, right? So for every input relation, we have to find a tree node that contains all the attributes of that relation. And the second property that's for the intermediate result size property is that each of the attributes, the bags containing it, have to be connected to each other. So what is the simplest tree that has those properties? Right, if you think a little, well, if you want to get rid of any kind of problems, make it really simple, put them all into one node. Right, so we have a tree that consists of a single node, let's call that tree T1. Every relation is there. They're obviously all covered now by that node. And obviously also trivially, every attribute is connected, right? And so in terms of the complexity, we can now run a worst case optimal join to compute that bag. And that's exactly the cost that the AGM bound gives us, which in this case is order n cubed for our 6th cycle. Right, so can we do better than that? And how could we do better? Intuitively, what makes that bag computation so expensive? It's that we have so many relations in that single bag. If we want to reduce the cost, we need to make these bags smaller. We want to have fewer relations in them. So here's the example from before. What if we create 2 nodes? One contains R1, R2, R3. The other one contains R4, R5, R6. We still satisfy both of the properties that we want. Every relation is covered, and all the attributes are connected. Right, you can see the only interesting ones are A4 and A1, which are appearing in both of these. The others appear in only one bag anyway. And now the good news is that by doing this decomposition, cost goes down to n squared, right? Because materializing, this is essentially a 3-path query in each of the nodes, takes only order n squared. Now let's take that a little further. Can we slim down the bags even more? Right, so if we got from 6 to 3, reducing computation time from n cubed to n squared, can we go all the way and maybe have only a single relation in every bag? Right, so now we would have O of n bag materialization cost, and that would be the best we can hope for. This is kind of how the Yannakakis algorithm looked like on the acyclic query. So what's the problem with that? Right, now let's look at our 2 properties. Every relation is still covered, but what about the attribute connectedness? Right, if you take a close look, it turns out A1 is not connected. It is appearing in R1 and R6, but nowhere in between. And this is creating a problem, like we saw in the example before for the 3 cycle, where we get these potentially large intermediate results. How do we get rid of that problem? Well, we simply have to somehow copy attribute A1 onto all these intermediate nodes to create this connectedness property. And what we do is essentially, we just add R1 to each of these intermediate relations, these intermediate bags here. Instead of the full R1, all we need is actually only the A1 attribute. Right, so if you think of it, for instance, if we look at this first bag up here, it is R2 joining with the A1 values in R1. Since these attributes are all different, this is a Cartesian product between the 2. Now, what is the cost of that Cartesian product? We could have up to n tuples in R2. There are up to n distinct values of A1 and R1. So we're back to an order n squared computation cost. Right? And so it turns out, even though we're slimming down these bags, we still have an n squared cost. And the question is, can we do better than that? Is that the final step? And how do we even figure out which of these trees in the end is the best? I'm going to skip that formal definition of tree decompositions and move ahead to just kind of in terms of if a query has multiple tree decompositions, how do we pick the winner? Right, so let's say in general, we have a tree decomposition that has order of L nodes. Each of them is materialized using a worst case optimal join algorithm, right? Now, based on the AGM bound, we know that the worst case output size, meaning the size of that resulting bag, is of the order n to the power di for some appropriate di that is greater or equal to 1. Since the cost of the largest bag is determining the complexity of the algorithm, we're interested in the largest d, so meaning the maximum of all the di over all these different bags. And that is called the fractional hypertree width, FHW. And it turns out if we know the fractional hypertree width of this decomposition, we know that the total bag materialization cost is in the order of n to the power d, and the size of each bag is also order of n to the power d. And if we run Yannakakis on such a corresponding tree, we know that it guarantees order n to the power d plus output size of the actual query complexity. Right, and this is exactly how these tree decompositions try to make an improvement over just applying a worst case optimal join algorithm on the entire given query directly. So who wins? In this case, we know that T1 has a bag size of n cubed, T2 and T3 have a bag size of n squared, and so T2 and T3 are kind of equally good, and T1 definitely loses out in this case. Notice that T1 is a special case where essentially we use the worst case optimal join directly on the query without any decomposition. So T1 loses because we do not really decompose, but between T2 and T3, are they really the same? And if we look closely, it somehow seems that T2 is not as good because it is actually joining 3 full relations in each of these bags, while T3 is only joining 2 relations per bag, and the second relation is only the A1 values of relation R1. So that somehow suggests that maybe there's some difference between them. And in particular, consider the following case. If we know something about the A1 values in R1, let's say we know they're not actually order n of them, but only order n to the 2/3 of them. So with this additional constraint, which we call a degree constraint, we can actually show that T3 does better than T2 on this kind of input where this degree constraint holds. So formally, the degree constraint that I just mentioned is shown up here in the upper right corner. And so let's look at that bag here, R2 versus R1, A1. If we know they're only n to the 2/3 A1 values, they're up to n tuples in R2, then we know that materializing this bag has a cost of O to the n 5/3. And similarly, the size of the bag is also just O to the n 5/3. So when we look at this entire tree decomposition T3, it turns out none of these nodes has a complexity higher than n to the 5/3. On the other hand, with the same degree constraints, our tree decomposition T2 is still quadratic. So if we know that A1 is not that frequent, it does not have that many distinct values, then we prefer T3 over T2. Now, consider also cases where T2 might win. Is that actually possible? If we look carefully, consider, for instance, the first bag of T2 that has R1 joining with R2 joining with R3. R2 has n tuples. If R2 has only a few tuples joining with each R1 tuple, and R3 has only a few tuples joining with each R2 tuple, you might actually be able to win. And so, for instance, if a few means something like n to the 1/3, right? So meaning every A1 tuple, every R1 tuple joins with only up to n to the 1/3 R2 tuples, and each of the R2 tuples joins with only up to n to the 1/3 R3 tuples. Formally, this is the degree constraint shown up here. And if we plug that in and look at T2, what happens is that we have order n tuples in R1, joining with n to the 1/3 at most in R2, with n to the 1/3 in R3. And so we're getting now n to the 5/3 guarantee for each of the bags in T2. With these same degree constraints, we still have order n squared complexity for these intermediate bags in T3. Right, so essentially, depending on the degree constraints, sometimes T2 wins, sometimes T3 wins. And one question is, can we get the best of both worlds by putting them together? Right? And so one idea is to say, why don't we treat each of these tree decompositions like a separate query plan? We take our input relations, we partition them appropriately, maybe copying some of these tuples, and then we send the right partitions to the right query plans. And if these query plans on these inputs have these kind of degree constraints, then we can win in the way that we just showed. And for our concrete example, the way to win is to do a heavy versus light decomposition based on the out degree of these tuples. To give you the intuition, let's call R1H the subset of R1 that contains only those tuples whose A1 values occur frequently. Where frequently means they occur more than n to the 1/3 times. So these are the heavy hitters of A1 values that occur a lot in the relation R1. With those, we can get for our tree decomposition T3 exactly the guarantee that we want. If we only join with R1 from the heavy hitters, we have our degree constraint of n to the 2/3 cardinality for each of these for these A1 values, and we're getting our n to the 5/3 guarantee. Now what is left? We only computed a part of the full join. So if we look at it, in addition to R1 heavy, there's also, let's call it R1 light, which is R1 minus the heavy tuples that we just removed and joined already. In order to compute the full result, we still need to compute that second part, which is joining the light R1 tuples with all the other relations. Now for that second part, we can use the same trick, but instead of applying it to R2, we apply it, instead of R1, we apply it to R2. And so this looks the same here. Now notice on the left, instead of R1, we have now R2 being copied on all these intermediate nodes. Essentially, we just cycle the indexes by 1, and it's the same idea. And now the corresponding T3 computes R1 light joining with R2 heavy, joining with R3 to R6. And again, the same cardinality constraint holds, but now on the R2 tuples, the A2 values. So what do we have now in total? I showed you two different query plans. Each of them uses T3. And we can do the same thing also for joining with the heavy R3s, the heavy R4s, the heavy R5s, and heavy R6. And after doing that, always using T3, what is missing to get the full result? Right? If you look carefully, the only thing missing is the leftover pieces joining with each other, which is the light ones from R1 with the lights from R2 and so on. Right? So these are all the leftover pieces. Unfortunately, for those now, the second degree constraint holds, the one that was good for T2. And so for that final join, we simply use T2 instead of T3 or T1 or any other tree decomposition. So what did we do in the end? We took that 6-cycle query. We created essentially 7 subqueries. 6 of them use T3, 1 of them uses T2. And by routing the tuples carefully to either of these, we were able to find out, we found a way that we never exceeded the backsize of n to the 5/3. And that means that when we run Yannakakis on the resulting relations that we get in these trees, we actually have a guarantee that the running time does not exceed n to the 5/3 plus the result size. And that's clearly better than the single tree complexity of n squared plus r, right? If you're using only T3 or only T2, I showed you that you can't do better than n squared because we had an example where n squared actually happened. And similarly, the worst case optimal join complexity would be even higher, it would be n cubed. And so for any join that has a smaller output than n to the 5/3, we have a clearly winning plan if you're using actually multiple tree decompositions. All right? And so the big picture is basically, if we apply worst case optimal joins directly to the query as it is given to us, then the complexity is determined by the AGM bound. If we decompose that query into these 3 decompositions where we have smaller bags that are cheaper to compute than the AGM bound would be for the full query, we can now get a better performance guarantee, which is based on the fractional hypertree width of the corresponding decomposition. And this in general reduces the time complexity, especially for more complex queries. And so the design goal here is to find the tree decomposition that has the smallest possible width, while still ensuring the 2 important properties that we have actually every relation covered by some bag and that the tree is attribute connected. And that actually makes it tricky. So it's not that easy to find these 2 decompositions, especially if you want to guarantee any kind of optimality. Now, if we have additional degree constraints, I showed you with the examples that it is possible to do better by exploiting those degree constraints. And degree constraints, they are generalizing cardinality constraints like that relations are at most of size n, and also functional dependencies. using those cardinality, those degree constraints, we can actually now show stronger performance guarantees, like I showed you in the example. So if we actually, even if we have a general input where we do not have anything more than cardinality constraints, by doing this decomposition into multiple query plans, we can still get a better performance. And the current frontier on that is what is called a submodular width decomposition. And so there's some algorithms that can achieve submodular width, and they're still pretty expensive, but this is something that is currently being worked on to actually find these decompositions more efficiently. If we actually have an input where we know that degree constraints hold for the entire input, even without these decompositions, we would already get better performance guarantees by using the right tree decompositions. And in general, we can actually hope for even better than just submodular width, which is now a degree-aware submodular width. And there's some citations that I have here to read more about how degree constraints are actually making an impact on these complexities. To summarize and to take a look beyond this part of the tutorial, essentially on acyclic conjunctive queries, the Yannakakis algorithm achieves the lower bound of input size plus output size in terms of running time complexity. And it does so with a simple one join at a time query plan. So it doesn't need anything fancy. It only needed these semi-join reductions to eliminate dangling tuples. Unfortunately, for general conjunctive queries, this lower bound cannot be matched. Worst case optimal joins achieve something that is now, it looks similar, but it is determined by the worst case output size of the join. And it also requires a more holistic multi-way join approach. So we cannot hope to achieve these worst case optimality guarantees by using binary join plans. And if we now, on top of the worst case optimal joins, use the tree decomposition, we can get an even better guarantee of into the D plus R, where the best D currently known is the submodular tree width. And in general, we can say, well, submodular width n to the power submodular width of Q is in the order of worst case complexity. But in practice, actually, it's a lot better, right? Because for most of the queries, it turns out to be, there's a significant asymptotic gap between submodular width n to the submodular width and the corresponding fractional the corresponding worst case complexity of the join. So for instance, for a 6 cycle, the worst case output size is n cubed, but with the 2 query plans that I showed you, using essentially T2 and T3, we can get n to the 5/3 plus R in complexity. Now, in terms of what is next, there has been actually interesting work on extending the model from full conjunctive queries to queries that have also projections and aggregation. There's a different direction that we can take by using factorized databases. So instead of trying to avoid large intermediate result sizes, factorized databases try to encode them efficiently to avoid this explicit large intermediate result size. And another interesting direction is to look at different stronger notions of optimality. So for instance, it is generally very difficult to try and match something like input size plus output size as a lower bound. So that lower bound is very impractical as a measuring stick for optimality. So instead, we can look at things like, for instance, only join algorithms that are comparison-based, and then try to come up with better lower bounds that are more realistic for those kind of algorithms. And we have many more other citations in our tutorial.